Tonight's speaker, who will be addressing us very shortly, is Professor Jain. He's a professor in physics in the Faculty of Science. Professor Pushpendra Jain joined the University of Botswana as a lecturer in 1987. Having risen through the ranks, he was promoted to the post of professor in 2004. Before coming to UB, Professor Jain had worked in Zambia, India, and the United States of America. Professor Jain holds a PhD degree in physics from the University of Connecticut in the United States, a BSc and Master Science degrees from India, and is a chartered physicist from the Institute of Physics in the UK. Trained as a theoretical condensed matter physicist, Professor Jain diversified to research areas in solar and energy, renewable energy, climate modeling, electronic microscopy, and fundamental physics. He has over 100 scholarly contributions to these areas of research through various outlets, such as refereed journals, publications, international, regional, and national conferences. And he has edited a number of works and published book chapters and done consultancies and technical reports in various fields and for various clients. He has co-authored 2 physics textbooks for undergraduate students. Professor Jain is the University of Botswana Node Coordinator of the African Material Science and Engineering Network, in short, AMSEN, of 5 African universities, most of them from this region, with an objective of developing human resources in material sciences and engineering through training at master's and doctoral degree levels. The network is funded by the Carnegie IS Prize in the USA, and presently there are 4 students who are sponsored under this network, and are all pursuing either the MPhil or PhD degrees here at UB. During his 23 years of service to the university, Professor Jain has taught most of the undergraduate courses and a number of MSc courses in physics, and has supervised students' projects and researches. Professor Jain is a member of a number of professional bodies and has served as a referee to peer-reviewed international journals, served on the board of a number of professional journals, and has been an external examiner at the regional universities. He has also been invited to deliver guest lectures locally, regionally, and internationally. Professor Jain has served as an interim chairperson of the Botswana National Committee of the World Energy Council, WEC, from 2002 to 2004. Professor Jain has received over 20 awards and honors during his student and professional career, of which the notable ones are 5 gold medals as an undergraduate and postgraduate student, 3 American Honor Societies memberships, and 3 research awards. Professor Jain is going to talk to us on a topic that has attracted so much attention and is currently at the center stage in the region. The topic of his lecture is Sustainable Development, Energy Matters. Read it whichever way you like. Both sustainable development and indeed energy do matter. Ladies and gentlemen, may I present to you Professor Jain.
Vice Chancellor, Deputy Vice Chancellor, Deans of the faculties, heads of the government departments and the representatives, excellencies, the heads of the diplomatic missions, the representatives, distinguished guests, fellow academics, colleagues, past and present students, friends and families, ladies and gentlemen. A very good evening to you all, and a warm welcome to this lecture event this evening. We begin our presentation with the interpretation of the title of the talk this evening. The title has 2 parts: Sustainable Development and Energy Matters. In the first part, sustainability is defined as human endeavor which meets the needs of current generation without jeopardizing the needs of future generations. In the context of energy, this can be stated as energy that is produced and used in ways that will support long-term human development in all its social, economic, and environmental dimensions. Development is an ongoing process to achieve industrialization, resulting in higher gross domestic product and increased per capita consumption of commercial energy. Increased access to education, healthcare, clean water, and expanded communication and transport networks are some of the outcomes of development, although the benefits are not necessarily evenly distributed throughout the population. The second part of the talk, energy matters, have dual meaning. The first meaning is issues relating to energy. And the second meaning is the energy does matter. It plays a role. So putting everything together, the title alludes to energy issues and the role of energy in sustainable development. In my presentation, I have inserted few such comics. They are not really comics, they are serious talk. They are issued by Energy Affairs Department and the Botswana Power Corporation, and they deal with energy conservation and energy efficiency. Ladies and gentlemen, energy conservation and energy efficiency is a serious matter. And I appeal to you, please conserve and as much energy as you possibly can. In addition to that, this is the Botswana component of my presentation this evening. Although I do not know the language, but that's my contribution to my lecture in Botswana. And if you can read it, very good. And if you cannot read it, these comics you will find in the daily news, they appear on and off. You'll see several of them in this presentation. Here is an outline of my presentation. It has been divided into 8 subtopics which are listed here. We'll go through these subtopics one by one and we'll go through the lecture. The first subtopic is energy and development. Here are 3 quotations. I'll tell you the importance of these 3 quotations. Let's read through them. The first one is, it is clear that there is some difference between ants. Some ends are energy are, while others are products which are additional to the energy are. It is 325 BC. Second one is, fire is the best of servants, but what a master, 1843. And the third one is, affordable energy in ample quantities is the lifeblood of the industrial society and a prerequisite for the economic development of the others. 2001. These three quotations spread over nearly 2.5 millennia, 325 BC to 2001. They all point to the pivotal role of energy in the development of human society. There are many aspects of development, namely social, cultural, and technological development, and economic development. We go on to the social, cultural, and technological development. The journey of social, cultural, and technological development of human race began with the discovery of fire. Some major milestones in this journey are listed here. I'll explain each milestone. Prior to the discovery of fire, human activities were limited to daylight only. Habitat was confined to warmer climates, and nights were dreaded for fear of predators. Discovery of fire provided protection from predators. Nighttime activities like singing, dancing, storytelling must have developed, and migration to colder climates would have started. That's how, from an energy point of view, that's how I see that the human culture must have developed. Further down the line, ability to tame animals provided animal power to ride and carry load. This increased the range of migration. The third industrial revolution has already started with rapid developments in mass communication and information technologies. Industrialization of less developed regions of the world and a quest to extend energy services to thus far energy destitutes to improve their living standards. Development of new and renewable sources of energy and associated technologies continue to be pursued to meet ever-increasing demand. These include solar, wind, tidal, geothermal, nuclear, etc. Access to right source of energy remains a prerequisite to all development initiatives. Be it the United Nations Millennium Development Goals of poverty reduction by 2015 or Republic of Botswana's Vision 2016 towards prosperity of all. For example, ladies and gentlemen, let me ask you, can we hope to reduce child and mother mortality at birth and extend complete health services without energy for lighting, sanitation, refrigeration, and storage of life-saving drugs? And I know your answer will be no. We have to have energy. Can there be eradication of universal poverty, hunger, and can universal primary education be achieved without energy for creation of jobs and self-employment opportunities, energy for lighting in the schools, teachers' residences, students' hostels, and for provision of transport? We cannot do without energy. Well, we come to the economic development aspect of the discussion. Economic development is an outcome of scientific and technological development leading to industrial development and revenue generation, which are fueled by sources of abundant energy, for example, extraction and value-added processing of raw materials, production of finished products, mass production of consumer and luxury goods, provision of services that generate revenue or add quality to life or both. Growth in global energy. This takes us to the energy demand, growth in global energy. This figure here shows the growth in energy demand with the growth in population. You can see this graph. Growth in population is this graph where you see the population, and the red line is the growth in energy demand for the last 150 years. And one thing we see right away for a layman, that as the population grows, the demand in energy grows. That's a very obvious observation, very obvious conclusion, nothing interesting about it. What is interesting is how the energy demand grows with the growth in population. I have divided this graph into 3 time periods as shown by these arrows. Arrow 1, arrow 2, time period 1, time period 2, and time period 3. In the first time period, which is up to early 1900, the growth in energy demand and growth in population are nearly linearly related in the same proportion. They grew in the same proportion. During this period, energy use was limited to basic needs of lighting, cooking, and heating. So, more population, more cooking, more lighting, more heat. From 1900 to 1970s, the demand for energy grew at a much faster rate than the population. This is a period of rapid industrialization. Motorized land, air, and marine transport grew. Living standards improved with corresponding increase in domestic energy consumption. From 1970s, energy demand grew at a slower rate than the growth of the population. You can see the energy demand curve is going down, where the population curve keeps on climbing. So from 1970 onwards, the energy demand grew at a slower rate than the population growth. This resulted from the oil crisis of 1972. Younger generation may not know about it, but those of us who are over 40 here will remember it very well. Resulting from the oil crisis in 1972, when greater measures in energy conservation were put in place to do more with less energy. So although the population grew, but we were able to save more energy through conservation measures, and the demand in energy growth grew at a slower rate. This takes us to the energy sources. Various schemes which are used to classify energy sources. I have shown here only 2 schemes. According to first scheme, we have traditional or low-grade energy sources. These are mainly used by poor populations which lack development. These sources are either free of cost or cost very little. They lack formal network of procurement and distribution. Commercial or high-grade energy sources, these are the fuels of choice for industrial use and for luxury living. They are produced and distributed through a formal network at a cost to consumer. Second scheme of classification is non-renewable sources. These resources, energy resources, have limited supply. When consumed, they are irreplaceable and will eventually run out of supply. Renewable energy sources, they have inexhaustible supply and continually renew. They will not run out of supply despite the growing rate of consumption. Following slide shows examples of various energy sources which are currently in use. Here are some examples of the traditional energy sources. The wood, dried cattle dung cakes, they are very useful source of energy in India. animal power, agricultural waste. But I would like to draw your attention to the middle picture. This is the example of energy efficiency as practiced by our ancestors. Much before the scientists and engineers coined the term energy efficiency. It did not even figure in the scientific literature till much later. Actually, in the field of energy, up to 1972, again I'm going back to the oil crisis, up to 1972, the energy efficiency and energy conservation were not issues at all. And energy was so cheap that nobody bothered. You will spend a gallon of petrol to go buy a packet of cigarette. That was the attitude towards energy till 1970. So we must be thankful to 1972, to the Arabs who woke us up to this reality. Fossil fuels are non-renewable commercial energy sources. They include coal, oil, and gas. And please keep your attention focused on these cartoons. They are of great national interest, and they are of great benefit to you also. Energy saved is money saved. On the next slide, we have some examples of renewable energy sources: solar energy, biofuel, tidal power, geothermal power, wind power, and biogas. And next slide has few examples of hydropower. It shows 3 applications of hydropower: a water wheel, a mini hydropower plant, and a large hydropower generation station. Fuel conversion provides man-made form of energy. Ladies and gentlemen, electricity is a man-made energy obtained through fuel conversion. And these energies can be renewable or non-renewable depending what input we use to produce these energies. For example, if electricity is generated from coal, oil, and gas, it's non-renewable. If it is generated from nuclear, hydro, solar, wind, geothermal, etc., it's renewable. And the next slide is charcoal production. In addition to these examples, there are several other energy sources. Unfortunately, we don't have time to discuss those in detail. I have just listed them here. Some of these energy sources have already been used and have very large applications. For example, nuclear fission. We know about nuclear power. Peat, tide, and tar sands and shale, waste dump gas. Some other energy sources, they are either in limited use or they are at different stages of research and development. For example, nuclear fusion is at an advanced stage of research and development. Hydrogen, fuel cells, combined heat and power, MHD generators, etc. are the other sources of energy or technology. There is a mixed bag here. Sources as well as technical. Ladies and gentlemen, because of the time restriction, this evening I will focus on solar energy only. For 3 reasons. Firstly, solar has the largest potential and is the most relevant to Botswana. Secondly, it is already in limited use in Botswana for lighting, space and water heating, refrigeration, water pumping, telecommunication, broadcasting, village electrification. And thirdly, ladies and gentlemen, this is the area of research to which I have made contributions. Solar energy. Here I would like to draw your attention to this graphic. Here are the artist's impression of the sun from various cultures from around the world. And it tells us that for all the cultures throughout the world, through all the periods humankind has lived, sun has always been seen as the sustainer of life. Otherwise, who would want to draw sun again and again in all the cultures? So there are two categories of solar technologies: solar thermal, which provides heat energy; solar photovoltaic, which generates directly electricity from solar energy. Solar devices can be non-concentrating, that is, they operate under one sun condition, directly under the sun, and they are used at fixed installation. And they are concentrating solar devices. In these devices, you collect the solar radiation from this much area and you focus it on a small device. And these devices must continually track the sun. They must follow the motion of the sun to keep the radiation focused on the device. Up to 5 sun, a single axis tracking is adequate. For more than 5 sun concentration, double axis tracking is essential, unavoidable. Ladies and gentlemen, the routine applications of solar energy, what we see around us in Botswana for the moment, I'm sure in future the picture will change. They are very well known to everybody. There is no point in discussing those ones. Everybody recognizes them, everybody is familiar with them, everybody knows how they work. So I have selected some other technologies which are not so well known to general public. Academics and engineers and technologists, of course, will know about them, but general public may not know about them. The first such technology is central receiver system, and an example is shown here. And I'm going to explain it to you. These systems produce extremely high temperature heat. Heat is used to generate power or for metallurgy work. A large number of large area plane mirrors in a field of several kilometers square, here, reflect radiation onto a central receiver. Each plane mirror, here we don't call them plane mirror, we call them heliostat, because they continuously track the sun to maintain focus on the receiver. The central receiver systems or power towers of capacity up to 10 megawatt electricity equivalent have been in use in many countries. One example is this 10 megawatt power tower in California, USA. It has 1,818 heliostat. Area of each heliostat is 39.3 square meter. Tower height is 80 meters. Heat is stored in 6,709 tons of rock, plus heat transfer oil, and plant can run at 7 megawatt power capacity for up to 4 hours from the stored heat. Here are some more examples of power towers, and still more examples. Unfortunately, we don't have to discuss each one, time to discuss each one of them. Next we go to passive solar architecture. In passive solar architecture, optimum use of solar energy is made for natural lighting and for improved indoor thermal comfort by controlled direct solar gain, selective absorption of solar energy, and controlled release of absorbed energy. Some design consideration for solar architecture are building orientation, window area and placement, exterior surface color, choice of building materials, etc. And if you do the right choices, then the result is improved indoor thermal comfort without the use of air conditioning devices, and you get natural day lighting with no or a very small extra cost of constructing the building. Overall, there is an overall saving in energy without any extra cost of construction. Buildings have been constructed in Botswana. For example, the Botek headquarters in Gaborone is a solar passive building. Some time back, I have carried out computer simulation to determine the influence of a number of building design parameters, which we mentioned in the earlier slide, on the thermal comfort of a medium cost BHC house in Botswana. The results are summarized in this graph. The last two bars represent the best case scenario. These two bars. We note that for the best case scenario, in which we have combined all the best parameters, if space conditioning devices are not used, you don't use air conditioning or heating, you will save 60% energy in winter time heating, and you will save 30% energy in summertime cooling. I also carried out the simulation of indoor temperatures without the use of air conditioning devices. What will be the temperatures inside with these parameters incorporated in the building, and the results showed a vast improvement of temperature by 2 to 3 degrees indoor temperature. A house which could be quite uncomfortable will be reasonably comfortable even if you don't have space conditioning devices. Unfortunately, I don't have space to show those results here, but the results are available in published literature. Next aspect of solar energy research is solar radiation simulation. Solar radiation data is essential for sizing of solar systems for specific applications. You need to know how much energy you are receiving so that you can decide what should be the size of your system. Where measured data is not available, one either uses data from a climatically identical location or generates it by simulation and modeling. Solar radiation simulation and modeling for Botswana has been done by myself with collaborators within the Faculty of Science. Modeling techniques developed are available in published literature. We are not going to discuss those details, but these techniques which we have developed, they include atmospheric transmission models, monovariate ARIMA models, bivariate models correlating extremum temperatures and solar radiation, and bivariate models correlating sunshine duration and solar radiation. I'll just give you a glimpse of how this works. I'll give you, in the next slide, I've shown the measured data, which I got it from the Department of Meteorology. The data form the basis of our bivariate models for extremum temperatures and solar radiation. Yeah, I don't need water. So the average monthly maximum temperature, average monthly minimum temperature, and average monthly solar radiation for 7 locations in Botswana. And gentlemen, you can straight away see that there is a correlation. One has to just sit down and find that correlation. And you have a model which correlates extremum temperatures to solar radiation, and using that model you can simulate solar radiation for similar locations, for other locations in Botswana. Important. Why everybody talks solar all the time? Solar radiation is the most abundant energy source distributed throughout the world, free from any political interference. there was oil crisis, but there will never be solar radiation crisis. In this graph, the red shades show the most intense radiation and lighter shades show the less intense radiation. Here is the scale of intensity. But what is important is, according to one study, if 8% efficient PV devices are used to cover only 7%, 7 out of 100, of the total desert area at 6 locations shown in the figure. Location 1, 2, 3, 4, 5, 6. You take those deserts, take their total area, cover 7% of that total area with 8% efficient solar devices, then those systems will produce 13,567 megaton oil equivalent of electricity, which is more than the total world energy consumption. Total energy consumption, not just electricity. More than the total world energy consumption in 2006, which was 741 megaton of oil equivalent. This slide shows these 6 deserts in Africa, Australia, China, Middle East, South America, and the USA. Here is the total area of these deserts. Here is the area which needs to be covered by the solar devices, and this is the percentage of each desert. We are going to focus our attention at the total. This is the total area of these 6 deserts, and this is the area which we have to cover with solar devices, and it is only 7%, ladies and gentlemen, shown here. Now the question is, a big question is, what are we doing? We are talking so much about solar energy. Why don't we act at this tip? Act fast and solve the energy crisis once for all. The answer to that question is in the next slide. Compare the cost of power generation from renewable energy technology. For various technologies, for the power generation cost per unit of electricity. Here is the regime of the wholesale power price range at present. This is a regime of retail consumer price range at present. If anything lies on this side of this regime, it's not cost effective. So we see solar photovoltaic is lying way outside the acceptable regime of the cost. It's way too expensive. It can be used for limited application. It can be used for specialized application. But you cannot have a mass power generation using these solar devices. It will be way too costly. You won't be able to sell it to the market. Now the question is, what are we doing? We are doing a lot. First thing we are doing is, there's extensive research is going on in improving the conversion efficiency of solar devices. This graph is taken from literature. This is too small to see, so I'm not going to explain this graph. What I'm going to tell is, this shows the improvement in the conversion efficiency from 1975 to 2010, over a quarter of a century. And vision efficiencies have improved vastly. If you look at this hand, they were lying right here, now they are lying right here. But even these conversion efficiencies are not cost effective. We need to do something. It is perhaps the thin film solar cells which will emerge as the winner in this race. Because thin film solar cells use very little of material, and that will bring down part of the cost. Second aspect of the R&D is, in addition to improvement of the efficiency of photovoltaic devices, a lot of research is going on in developing less costly materials, in developing new kind of devices, in developing new technologies to manufacture those devices. And some examples are shown here. We have paint-on and spray-on solar cells. These all are the experimental stage. We have carbon nanotube solar cells. We have plastic solar cells. I could not find a good picture of it. And we have hybrid solar cells. I couldn't find a good picture of it. And here's a picture, new technology. This represents new technology, manufacturing technologies. New manufacturing technologies are being developed to bring down the cost. Ladies and gentlemen, another reason for low dissemination of solar devices in developing countries like Botswana is the shortage of trained manpower for maintenance of systems and choice of inappropriate systems because of lack of information and understanding. That's why the systems fail. To bridge the training gap, the Department of Energy, Government of Botswana, had commissioned a study on the training programs that are needed within the country. This study was taken by myself together with a colleague, and the recommendations can be put together in three categories. In the first category of recommendation, we recommended that short courses should be introduced to upgrade the skills of existing plumbers and electricians to NCC and HND qualifications in energy. Third recommendation was for the new intake. New intake of students must begin at C certificate level in electrical and plumbing, and going through the process, they should finally end up with a HND in energy technology. Third recommendation was modules and courses for secondary education, tertiary programs, managerial training, consumer education programs, public awareness programs. Ladies and gentlemen, more often than not, wrong products are bought when they are bought through tender, and when the tenders are evaluated by those people who do not understand the system, who do not understand the technology. That's why we recommended managerial training is a very important aspect of if we want to make solar energy a success in the country. Well, these few slides, I mentioned what I have done when I came to Botswana 23 years ago. But prior to that, also I was involved in solar energy research and development for 7 years in India and 4 years in Zambia. There, my work was involved silicon cell materials preparation, device fabrication, single axis clockwork solar tracker as listed here. Interesting thing to notice, one of our technology was transferred to the industry, and I enjoyed some royalties from that. And another work was recognized by the Rolex Award of Enterprise in 1980. Now, we come to the fifth section. I told you about 8 sections. We came to the fifth topic, world energy consumption. Here, we will analyze the variation in total and per capita energy consumption, energy mix, sector-wise energy usage, energy intensity are analyzed. I would like to emphasize that industrialized countries consume significantly more energy than the less developed and developing countries. Here, as you can see, ladies and gentlemen, developed countries, which have only about 21% of the world population, they consume 60% of the world energy. Developing countries, which have about 79% of the world population, they consume only about 40% of the world energy. This aspect is further emphasized in the next slide. In this slide, ladies and gentlemen, what I'm trying to show is, we have plotted per capita GDP in US dollar and per capita consumption of energy in gigajoule. The countries which have the highest GDP are also the highest consumer of energy. The countries which have low GDP, they consume low energy. Most of the countries of Africa lie in this part of the graph. Continuing on the same topic, this slide shows per capita total energy consumption for some regions of the world. The blue bar is for the world average. These maroon bars are for some of the regions of the world: North America, Europe, Middle East and Northern Africa, Central America and Caribbean, South America, Asia. Green bars are for developed countries and developing countries. See the disparity. Per capita total energy consumption. And next, the purple bars are high income countries, middle income countries, low income countries, and the last bar is our very own Botswana. Ladies and gentlemen, for the next 4 slides, I would like you to keep your attention focused on the purple bars together with the orange bar for Botswana. Well, from these 5 slides, I want to bring out one important point. This is the per capita residential energy consumption. This is per capita electricity consumption. This is per capita petrol consumption. And this is per capita diesel consumption. From these 5 graphs, ladies and gentlemen, there are 2 things you would have noted. The pattern has remained the same throughout the graphs. But very importantly, Botswana mimics middle income countries. And this is what we are told by economists by doing a lot of fancy economics. We did not do anything fancy. Only per capita energy consumption, it tells us Botswana has to be a middle income country. It can't be any other way. So, ladies and gentlemen, at this stage, I would like to give a message to our young audience present here for the future potential leaders. If you want to take Botswana to the next stage of high-income country, start using more energy. Not just driving around, just listen to me. More energy in industrial activities, more energy for revenue generating activities, more energy for to provide value-added services. Let's develop that. Then we will consume more energy and will rank the high-income country. Listed here is wood, oil, coal, gas, hydro, nuclear, and other. And for some of the regions of the world. Here what you are seeing is, in Africa, a large proportion of energy is provided by wood. And you remember it's a traditional energy source. Whereas in North America, only about 3% of the energy is provided by wood. You can see the same as, unfortunately, those graphs are not here. We see in sub-Saharan Africa, a large proportion of energy is used for the domestic sector. That does not mean that the standard of living in sub-Saharan Africa are very high. No, ladies and gentlemen. What is happening here? We talked earlier, in Africa, a large proportion of energy is supplied by wood. And all that energy is going for the domestic sector. There is very little industrial activity. Transport sector is also not well developed. Wherever you look at North America, it has it consumes a lot of energy, and a fair proportion goes to industry, fair proportion goes to transport, fair proportion goes to residential sector, etc. You see here, developed countries, they use less proportion of domestic energy. Developing countries, a large proportion is used for the residential sector. Energy supply and use on Botswana. Ladies and gentlemen, this is a lecture on its own, and we don't have time to go in details. This only summarizes the various sources of energy which are used in Botswana: imported electricity, petroleum products, wood, and in my country it is solar. Because I'm too close to it. And these are the various sectors: residential, government, industry, agriculture, and transport, how it is used. However, if you have the Botswana National Atlas, it has a variation of this chart in the chapter on energy, and that chapter was done by myself with input from colleagues. If you don't have it, you can still buy it from the Lands and Surveys. It is a beautiful atlas. It covers various aspects of Botswana economy, and energy is one of the chapters by myself and colleagues. That means how effectively the energy is used. Energy intensity is the energy used to generate 1 unit of GDP in products and services. Energy intensity depends on the sector of the economy. Some of the sectors are energy intensive, like industry, and some of the sectors may not be as energy intensive, like the services sector. So if we really need to analyze the energy intensity, we will have to look at each sector. And since we don't have time, we decided to look at the overall energy intensity of some of the regions of the world. Overall energy intensity is, you take the total energy, divide by the revenue generated, and then you have the energy used per unit of revenue generated. Done earlier, developing, high income, middle income, low income, and for 3 sample years, 1990, 2000, 2003. You might be thinking, what is 2003 doing here? Why not 2010? The energy data, their collection and analysis take time. They have to come from various countries. They get collected at a central location. They analyze, they validate it. So by the time they are released, there is a time gap of a couple of years. So 2000 years is the latest available data. 2 things we note here, rather 3 things. From 1990 to 2003, energy intensity has improved. That is the result of improvement in energy efficiency. Another thing we note here is energy intensity for low-income group countries still remains high, whereas the energy intensity of high-income countries is low, which means high-income countries are using their energy more wisely. With less energy, they are able to produce more revenue, whereas the low-income countries, they use a lot of energy to produce same amount of revenue. And look at sub-Saharan Africa. That is criminal. Using this much of energy to produce unit dollar worth of products and services, what is going on here? Well, that makes a big discussion, and we don't have, I'll leave you with this question to think about it. And what can be done? Machineries are old, they are not efficient, they break down. The large energy is supplied by fuel wood, which is used in the houses, because it's overall efficiency, and so many other things. In the 6th topic, we talk about environmental degradation and energy. While energy has helped us to develop, we have come a long way from being to being the people who are traveling in the space, landing on other planets and satellites. But at the same time, it has brought a lot of things. You hear all the time of climate change, glaciers melting, and all those. And that is because at present the world energy comprises of 80% fossil fuels, 10% biomass, and they all contribute to degradation of air, land, and water. Among atmospheric pollution, we have greenhouse gases. About 68% of the worldwide greenhouse gases are energy generated. We have non-greenhouse house emissions, and we have suspended particulate matter, volatile organic compounds. Water pollution comprises of acid rain, pollution of oceans, surface and groundwater pollution. Here, there is an interesting story I came across about acid rain. In some cities of China, acid rain is so severe that the bus stop signs have to be changed every few years. And land degradation includes deforestation, desertification, acid rain leaching, waste disposal, etc. This topic itself, ladies and gentlemen, is 5 lectures worth. So we'll have to move on. Radioactive pollution, of course, we all know, results from nuclear power stations, accidental leakage, or nuclear accident, like the one we had, when was it? 1986. That's the most disastrous nuclear accident in Chernobyl in 1986. Here are some examples of how we are killing our environment. Pollution of the environment, land degradation, water pollution. But here, I would like to draw your attention to this. This is not a very uncommon sight on our roads. We all know in Botswana, there are heavy fines for various traffic violations. Heavy fines. But this is just fine. Energy security and sustainability. At present, the world energy consumption, there are many ways of putting these things together. And now I have put the world energy consumption differently. It comprises of 17% of electricity, 44% of low temperature heat, 10% of high temperature industrial heat, and 29% of transportation fuels. About 2 billion people worldwide have no energy services. Another 2 billion have inadequate and unreliable energy services. Energy poverty prevails predominantly in developing and underdeveloped countries. We continue. There is an uneven distribution of predominantly used energy sources amongst the countries of the world. These are the fossil fuels. As developing countries embark on development, their energy demand will grow at a faster rate than that of the developed countries, because they have reached a kind of a plateau. And a large fraction of it should be supplied by commercial sources. The graph in the next slide gives 4 scenarios of energy demand projected up to 2100, considering various combinations of consumption. It's all theoretical work. You can assume anything and you come up with a scenario and you come up with a projection. The various assumptions are population and industrial growth, technological development, resource availability, environmental pressures, etc. And here's the graph, ladies and gentlemen. Unfortunately, it's taken from literature, not my literature, from somebody else's literature. And there are 4 scenarios. This scenario 1, scenario 2, scenario 3, scenario 4. And each one of them gives us energy demand from 2000 to 2100. Unfortunately, the discussion of this graph is in the next slide. From the graph we note, energy demand shall continue to grow. Nothing very brilliant. It's an obvious thing. We all know it. Fossil fuels shall continue to play an important role in the world energy mix. The contribution of renewable energy technologies shall also increase. Considering all these factors, countries will have to meet the increasing demand of energy with a mix of sources that may not be available within their borders. Under these circumstances, one cannot talk of self-sufficiency in energy. You can talk of self-sufficiency in food. You can talk of self-sufficiency in clothing industry. But you cannot talk of self-sufficiency in energy. Rather, energy security and sustainability shall be the guiding factors. And when it comes to energy security, it is not only the developing countries whose energy security can be threatened. Even the energy securities of the developed countries can be threatened. Or of a region can be threatened. Instability and conflicts in regions where energy sources are concentrated. We hear of Iraq war, we have Kuwait war. Using energy supply as a weapon of negotiation and war. We have seen wars in these areas. Military action to secure energy supply. Natural calamities affecting energy production and supply. Breakdown in the energy production and supply chain. Inadequate investment in the energy production and distribution sector. Ladies and gentlemen, we all know we are experiencing electricity crisis in Botswana. Because all said and done, there is inadequate investment in the sector. We relied on South Africa, and now South Africa says, no, thank you, we don't have it. Terrorist threat targeting energy production and supply, that has become a major issue these days. They can come and blow your power station and you have it. Market volatility. To counter these threats and to attain energy security and sustainability, countries must take some measures. And these measures are here, ladies and gentlemen. Increase domestic production and rely as much as possible on indigenous sources. Diversify the energy mix so as not to depend heavily on any one source and on energy import. You cannot avoid it completely, but minimize it. Hold 90 days reserve of imports in the previous year. And in case of disruption of 7% or more in supply, share reserves with IEA member countries. IEA stands for International Energy Agency, and this is a recommendation by IEA. A strong regional cooperation in energy must be forged through trade treaties and infrastructure linkages. We know we have South African power. Southern African power, my apologies. Energy conservation and efficiency must be continually improved to make that last drop go an extra mile. Fossil fuels shall continue to dominate, and as the fuel prices shall soar with reserve depletion and demand, all reserves which were uneconomic to mine shall become economically viable and shall be reopened. will have to go deeper, farther, and to more remote locations in search of new results. We have in Olympics, we have faster, higher, and all those things. Same applies here. We'll have to go deeper, farther, and more remote locations to search new results. Let's use unconventional sources like peat, tar, and tight sand, and shale shall have to be exploited fully. If we do not act wisely, then demand this is our future. We will have cars, but they will be driven differently. Ladies and gentlemen, energy is a very complex, multidisciplinary field, like a three-dimensional jigsaw puzzle. This evening, we could glimpse only a few pieces of the puzzle, which revealed only a small corner of the picture. Many more pieces still remain hidden from the view. However, in the interest of time, we must move on to the last, but my very pleasant duty of acknowledgement and thank you. Acknowledgement one. All the photo credits are here. I'm not going to read them. Data credits are here, but here I'll try to emphasize a few things. University of Botswana. During my 23 years of service, I have gone through a lot of changes. Three major changes in the executive management, many changes at faculty levels, many changes at head of the department level, but there was one thing common to all these administrations. They provided excellent environment for professional growth and development. There is not a day in the history of this university where even a single academic can complain that he could not do this thing because university administration interfered with his own hard work. So I thank all the structures of the university from 1987 to date. However, ladies and gentlemen, I would specifically like to sincerely acknowledge two persons from the very first management of the University of Botswana. And those two persons are Professor Thomas Blue, then Vice Chancellor of the University of Botswana, and Mr. D.D. Kuhlman, whom I met on my first day on my arrival in Botswana. These two gentlemen, their welcome and help in settling down was unparalleled, which I had not experienced elsewhere. Maybe that is why I lasted here 20 years. I just fell in love with the place. Department of Extramural Activities and Public Education Department, CC is thanked for organizing the event this evening, and I would particularly like to thank Dr. Gangappa and Dr. Ramola Mabane, who took personal interest and personal initiative to make this evening a success. My colleagues and friends are acknowledged. Students, past and present, they are acknowledged. Mr. Stephen Corsier, who was struggling with the setting up. If we did not community, see, when you live in a community, you need the support of your community. My community friends and families are very sincerely acknowledged. I cannot name them all, but they are too numerous, and I owe so much thanks to each one of them. And some of them are present here this evening. I thank you all, ladies and gentlemen, for attention and attendance. But more than that, I will be failing my duties if I did not acknowledge my family by name, who provided me support throughout my life. My wife, Mrs. Dr. Preeti Jain, first daughter Gauri, and her husband Brendan, second daughter Shilpi, and son Shitesh. the very last, ladies and gentlemen, I pay tribute to our beautiful UB campus. This is the place which provided me opportunity to become what I am today. This is the place where I grew from a young man 23 years ago into a mature academic. This is the place where I spent my entire productive life as a contract worker with a diminished sense of belonging. This is the place which I have seen grow in a quarter of a century from a small, dusty, college-like campus into a grand university, world-class university it is today. And this is the place where our about 15,000 students have passed through my classes in this quarter of a century, and many of them are here present in the audience holding senior government positions. And it is now their children who are beginning to return to my classes. That is my greatest satisfaction, ladies and gentlemen. I thank you all once again. Kila boha bogarsu.
Vice Chancellor, Professor Utlurile, Deputy Vice Chancellor, Professor Youngman, Your Excellencies, representatives of the diplomatic corps, and your spouses, former chair of UB Council, Rempo Tokwane and Mrs. Tokwane, invited guests, colleagues, students, here I'll say all protocol observed. Good evening to you all. Well, by practice, there are no questions after such a lecture. But I anticipate that the lecture will stimulate discussions and debates among ourselves and with the presenter. Certainly we have been given a deeper understanding of the role of energy in sustainable development. The very title of today's lecture, Sustainable Development, Energy Matters, is a reflection of the subject that energy is an essential component of economic development.
I finished my 68. From cooling outdoors. All that air conditioning and the windows open, it's a beautiful contradiction,
Energy.
No sense. It's about energy and you're doing nothing about it. Thanks so much.
You look better in person. You look better in person. All this gone. And this is like, hello, good evening.
Nice to see you. Children. You're all very recognizable.
Because you saw saw the pictures.
No, because we saw you.
Okay.
Thank you.